We'll be looking at a dynamic pulley problem in this question. In this question we have a simple pulley system, which is basically just a disc here with a string or a rope going around it, and tied to that rope is some mass which we're labeling here m sub 2. Keep in mind that unless stated otherwise in the question, that you can usually make certain assumptions in pulley problems like this one. You assume first of all that there's no friction between the rope and the pulley system. There's no friction between this rope and this disc. You assume that the pulley system itself here, the disc and the rope, are usually massless. And you assume that the rope is tight at all points, meaning that there's no slack portions of the rope. And in other words, the tension through every point of the rope must be equal. Now, we previously looked at the static case of a pulley situation. So in the static case, we have this pulley system with this mass connected to it, which is some height above the ground. You can assume the ground is somewhere down below here. And obviously, if the situation is static, then this mass isn't moving. It's not moving left, right, or up or down. And so in other words, there has to be an upward force that balances out the downward force of gravity. What makes pulleys useful is that the upward force you have to apply is less than the regular upward force you'd have to apply if you were just holding this object directly up. Let's say that the downward force on m2 due to gravity was 100 newtons. So if you were holding m2 yourself, you'd have to apply 100 newtons upwards to keep this in place. On the other hand, in a pulley question like this one, the actual upward force that that the rope has to apply upwards is only 50 newtons. And the reason for that is because over here we have a portion of the rope, and over here we have a portion of the rope. And both of these portions they point upwards. They apply an upward force. So if you represent the force as T for tension, then that tells you that 2T minus mg equals 0, and from Newton's second law. And so T is just equal to mg divided by 2, which would be 50 newtons, again, in the static case. And once again, that comes from the assumption that the rope is tight throughout all points. It's taut. So now we'll be looking at the dynamic case where this mass m2 can move up or down. It's not going to be moving left or right, but only up or down. So obviously one way that you can imagine this going down is if it's just falling. If it's either in free fall or if the mass is greater than the support of the rope, then this would be moving down. But you can also imagine this mass moving up by imagining an upward force pulling on this portion of the string. You can imagine a force being applied upward at this blue point here and pulling this up, which in turn pulls m2 up. So we're going to do something interesting here, and we're going to actually add a second part to this system by adding another pulley. So here you can see that the rope is now connected and goes around another pulley, which in turn is connected to another mass m1. And you should convince yourself that in the case of this mass being pulled up by applying a force upwards, that's the same as if m1 itself was falling down. Because if m1 was falling, then it's obviously going to be pulling this rope up along with it, which pulls m2. So the question now becomes, what is the relationship between the masses m1 and m2, which correspond to whether m2 moves up, down, or stays in place? So to start solving this problem, the first thing we want to do is we want to draw a free body diagram for the system. We want to draw any forces that we know should play a role. We'll take down as moving along the negative y direction or whatever axis, and up is the positive direction. So the first force vectors we can draw are those due to gravity, m sub 2g and m sub 1g, the force of gravity on this object and on this object. Now keep in mind that this is all one rope from here going around this pulley and around the second pulley down to m1. And in the static case, as we said before, there's two sections of the rope that apply an upward force T. There's this section here and this section here. But we also have on m1, we have another section where the tension points up. So we can draw the force vectors due to the rope as so. And remember, because this is all the same rope, and because we said that the rope is taut, meaning that the tension is the same throughout all points of the rope, that tells us that these tensions, the magnitude and the direction obviously, have to be the same. So this value of T equals this value of T equals this value of T. So now that we drew the force vectors, the free body diagram, that will help us write Newton's second law for the system by looking at all the net forces on each object, the net forces on m1 and on m2. So the net forces on m1, we know we have minus m1g, the force due to gravity, and we only have one tension force, only have plus T, and that's going to be equal to the mass of this object times its acceleration. So we have minus m1g plus t equals m1a1. On the other hand, for m2, we again have the downward force of gravity minus m2g, but we have two tension forces, the same as in the static case, remember? So we have minus m2g plus 2t equals m2a2. So to analyze this problem, what we really want to do is we want to find the relationship of A, the acceleration of either object, depending on the masses, as well as maybe the relationship of t. And we have our two equations from Newton's second law for each object. And the question is, so what's the relationship between A1 and A2? I just used the subscripts A1 and A2 to be pedantic. But what about the actual relationships of A1 and A2, either in magnitude or direction? We saw in other questions where oftentimes when we have multiple objects that make up a system, then the accelerations are the same. So can we say that in this case? Well, first, the relationship between the directions of A1 and A2 should be obvious, because we know you can easily visualize that if M1 is falling down, then M2 is moving up, and vice versa. If M2 is moving down, then M1 is moving up. So the signs of A1 and A2 have to be opposite. What about the actual magnitudes of A1 and A2? Will they be a one-to-one relationship? Will it be something else? Will it depend on what the masses are? So to answer that, let's actually draw a series of horizontal lines. So here we have some horizontal lines, and notice that M1, the top of M1 and the top of this disk, or our first pulley system, are aligned with this dashed line here. Keep in mind that obviously this disk here, which makes up the first pulley, and M2, they're basically, you can treat them as the same object because they're going to move up and down at the same rate. Let me remove the forces, the force vectors, so you can see better. And let's now run a simulation to see how these objects move. First, we'll do the case where M2 moves up and M1 moves down. So let's run it. And you can see they begin moving. And let's stop it here. So the top of M1, which again started off over here, aligned with this dashed line, has moved down one bar. These bars, by the way, are equidistant. And so we can see it move from here down below one bar. Whereas the top of this pulley system, which again was aligned with the top of M1, has only moved half of a bar. In other words, the distance traveled by M1 and M2 in the vertical direction is not the same given the same amount of time, which tells us that the accelerations have to be different. The magnitudes have to be different. Let's now look at the case when M2 moves down and M1 moves up. To do that, I have to change the masses. Let me first reset it, and let me lower M1. Or let me actually even raise M2 to be a bit bigger. So again, notice that these 2 points here are aligned, the top of M1 and the top of this pulley system. And now let's run the animation. Okay, so you can see that this object, M1, which started off here, it now moved up 2 bars. It moved up this bar and this bar, whereas the top of this M2 pulley system moved down only 1 bar. So in other words, this object here, M1, covered twice the distance that this object here covered, and obviously the directions are opposite. So we know that the magnitudes, that magnitude of one will be 1/2 the magnitude of the other. Namely, A1, the acceleration of this object, is 2 times the acceleration of this object and in the opposite direction. A sub 1 equals minus 2A sub 2. So we have 3 equations to now work with. We have this equation, and this equation. And we can substitute this into one of these equations and solve for the relationship of either of the accelerations with relation to the masses of M1 and M2. Keep in mind that this relationship between A1 and A2, that itself does not depend on the masses. So now to find the actual acceleration, let's find the acceleration of A2, A sub 2, depending on the masses. It makes sense because, again, initially we were just looking at the single pulley system, the acceleration of this object. So to find that relationship, we can first multiply this equation by 2, and then subtract these 2 equations from one another to eliminate t, and then we'll have minus m sub 2g plus 2m sub 1g equals m2a2 minus 2m1a1. Again, we just multiplied this by 2 and subtracted it from this equation. And then we can substitute in this for a1, and we have 4m sub 1 plus m sub 2 times a2. Dividing this equation by this term in parentheses, we get that a2 equals 2m1 minus m2 divided by 4m1 plus m2, and all of that times g. It's not obvious that this would be the answer, so let's check to see if it actually makes any sense. And we can do this by looking at the extreme cases. First, we can look at the case where m1 is very, very small or approaches 0. When m1 approaches 0, then this term here goes to 0, and this term goes to 0, so we have minus m2 over plus m2 times g, and obviously the m2's cancel, and we have minus g equals a sub 2. And that should make sense because if this is 0, then basically this object is just in free fall. Remember that the mass of this object is equivalent to the upward force that you apply if you pull directly on this rope. So with no upward force, no resisting force, then this object should be in free fall. What about the case where m2 is very small, at least compared to m1? So again, we look at the limiting case and we now plug in for m2, that's going to be 0. And we have 2m1 over 4m1 times g. M1's cancel, you have 1/2 g equals a sub 2, which again equals minus 1/2 of a sub 1. And that is the same result as we have over here. If you multiply this by 2, you have 2a sub 2 equals minus a sub 1. The same result as we would expect. Now, what about the static case where m1 and m2 are both not moving? That happens, as you can see here, this denominator can never equal 0 because we have, as long as the masses are not 0, which if both of them were 0, then we wouldn't have anything to look at. But if the masses aren't 0, then the denominator can't disappear. But the numerator can disappear when m2 equals 2m1. So that tells us that in the static case, the mass of this object is going to be 1/2 the mass of this object. We have m1 equals 0.5 m2. And we have, again, the numerator goes to 0, and the acceleration equals 0. And this result shouldn't come as a big surprise because remember, in the static case, we know that if the downward force on m2 was 100 newtons, then the upward force that we'd have to apply to keep this in place would just be 50 newtons. So you can imagine that if this weighed 100 kilograms, then the upward force you'd have to apply would just be 50 kilograms times g, so m1 just has to be 50 kilograms. So now let's actually find a relationship for the tension as dependent on the masses. And to do that, we want to isolate t. So we can subtract from this equation from this equation. So we have 2t minus t gives us t, and then everything else, this minus this. So the equation starts off looking more or less like this. And you can solve it and see for yourself, it's just basic algebra, that in the end you should get that t equals m1 m2 divided by 4m1 plus m2 times 3g. And again, we want to see if this answer actually makes sense. So first, let's look at the units to make sure that they make sense. And they do. We have two masses multiplied by each other. We have the units of mass is kilograms, so kilogram times kilogram is kilogram squared. Divided by kilogram plus kilogram is just kilogram. And the units of g is just meters per second squared. And so we have kilograms times meters over a second squared, which the units of that is the same as newtons. So the units work out. And now let's look at one of the extreme cases. Again, let's look at the static case, when we know that m1 equals 1/2 of m2. So we can plug in for m2, let's plug in 2 times m1. And we have m1 times 2m1 over 4m1 plus 2m1 times 3g. That's the same as 2 over 6 m1 squared over m1 times 3g. Simplifies as m1 over 3 times 3g, which is the same as m1g, which equals t. And that should make sense to you because, again, all we're saying is that, again, we know that for this object, there's only one upward force t. And so if you plug in m1g for t, you get minus m1g plus m1g equals 0, the static case. Likewise, you can do the same by plugging in you can plug in m2 for m sub 1, and you get that the upward force in terms of m2 is going to be 1/2 m2g. And again, if you plug this into this equation, then again you get that the net acceleration equals 0, as in the static case. And there you go. We're done with this problem, with this question. It's a little bit of a tricky question, but hopefully it wasn't too difficult. If any parts didn't make total sense, and go back, make sure you understand every little detail. And with that, we can move on to the next problem.